So welcome to the third part of today's lecture on complex numbers. What we want to do now is just kind of stop and take a step back and talk about a geometric way of representing complex numbers. So it's useful for this course, but it will definitely be useful for your upper year courses where you learn about complex numbers. And we're also going to use this geometric interpretation to come up with a different way of representing a complex number, namely polar coordinates. So the big idea about representing complex numbers is to draw them in the plane in the following way. So you have a complex number a and bi, and you're going to make a plane where on the plane you're going to put the real part of z on the x-axis, and on the y-axis you'll put the imaginary part of z. So if I were to take the point a plus bi, I would say, well, here's the real part, A, and here is the imaginary part, B. And so I would represent the complex number Z by this particular vector, or sometimes you just represent it by a particular point. Now, why is this interesting? Is because you can actually start seeing where the conjugate and the modulus is showing up. We'll start with the modulus, because if you look at the length of this vector using the Pythagorean theorem, you know that the length of this vector is the square root of a squared plus b squared. But that's just by definition the modulus, right? So this is the modulus. So the modulus is actually telling us something about length of the vector if we were to plot it in the complex plane. And what is the conjugate doing? Well, the conjugate switches your sign. So I didn't really make this to scale. 1, 2, 3, 4. 1, 2, 3, 4. So minus b is right here. And so the conjugate is what you get when you flip the vector around the x-axis. So this is z equals a minus bi. And then so what we have here is that the conjugate is a reflection. So that's kind of geometrically what's happening when we look at both the conjugate and the modulus in terms of plotting the points in the complex plane. So this is usually called the complex plane, where we're using the x-axis with the real part and then the imaginary axis or the y-axis for the imaginary part. Okay. Now, if we look at this diagram here, there's actually different ways of representing this particular vector, right? So let me plot the vector again. So here's A, and let's say this is B, and let's draw my complex number, and Z is equal to BI. So there's two ways of getting at this particular point. So I can use the Cartesian coordinate system where I tell you how many units left or right I go and how many units up or down that I move. However, there's a different way of getting at this information, which is thinking about what's the degree that I move this vector up from the x-axis, and then I need to know the length of this vector. So this complex number can be determined in terms of a and b, but it could also be determined in terms of this angle and the length of this vector. And not only that, we can now relate some of this information, right? So we have that A should be the length of Z times the cos of theta, the angle, and B is the length of Z, or this vector, times sine of theta. So we're just using kind of some basic trigonometry. So this gives us what's called the polar form of our complex number. And the polar form is defined to be usually written as the length of Z times cos theta plus the length of Z times sine theta times our imaginary number I. Now sometimes this is just written as in the following form, the length of Z times cos theta plus I times sine theta. And depending upon your book, right, there's kind of a lot of there's a lot of information here, but really you only need the theta. So sometimes this is written as the modulus times CIS of theta. So CIS theta means the cos of theta plus the imaginary part of theta. So this is called the polar form, where instead of using the A and B, the regular Cartesian system, we're using the angle and the length as the vector. Now this angle is called the argument of the complex number. So the theta is called the argument, and you can compute it in two different ways. You have that if you want to compute it, it's equal to the inverse of cos of A divided by its modulus, but it's also equal to the inverse sine of B divided by the modulus of Z. Both of these numbers are the same. So let me just illustrate quickly how to write a complex number in polar form. Okay, so the modulus is probably the easy part. So the length of Z is 1 squared plus the square root of 3 squared, and then take its square root. And so downstairs I'm getting 1 plus 3, which is the square root of 4, which is 2. So that gives me the modulus. And now I need the argument. So the argument is going to be cos of inverse of 1 over 2. And in radians, that is pi 3, right, which is 60 degrees, because I'm using a 30, 60, 90 triangle. So putting the pieces together, our complex number Z, which is 1 plus root 3i, could also be written as 2 times cos pi 3 plus I sine pi over 3. Okay, and as a picture here, let's see if I can draw it to scale. This is where 1 would be. No, 1 would be a little closer. Let's try it again. Here's 1, and root 3 is right here. So there's my complex number Z, which is equal to 1 plus root 3i. And then this angle right here between, this angle is pi over 3. And then the length of this vector is 2. So the modulus of Z is equal to 2. So that's an example of writing a complex number in polar form, and I'm sure your homework will have many questions where you're supposed to get this information. So what's the advantage? Well, one of the big advantages of using the polar form is that division and multiplication becomes a little bit easier to work with. And let me just write out the formulas in this case. So if you're given one complex number, Z1, so here is its modulus, R1, and then its angles, theta1, and then Z2, you're given the R2 and the theta2. How do you define the multiplication of these two complex numbers? Well, you're multiplying their lengths, their modulus together, and what you're doing is, for their argument, you're just adding the two arguments together. So that's how you can easily multiply complex numbers together. And dividing is kind of similar. You take the moduli, or the modulus, I guess moduli, and you divide them. And for the arguments, you're subtracting one from the other. And there you go. That's one of the big advantages that personally I think that you get from polar form, is that these operations become easier to work with. So there we'll take a brief pause, and then in our last part we'll look at start bringing in complex numbers into linear algebra.